welcome everyone. So, let me erase this so I can show you something. Alright, so today I'm going to show you a video tutorial about how to find the voltage from a point, or at a point from a distance away from the center of a circular ring, charged circular ring. So if we want to do this, we first should understand how to find the voltage with just one point, right? So we have this, let's say that we call this Q, right? We call this point P, P prime. And so let's call the distance between them, let's call it, R. So the question is, how do you find the voltage at point P prime relative to this charge? Well, what we do is we can just, we use the formula, the Coulomb's constant times the charge divided by the distance between the point and the charge, the point charge. Now, this is theoretically like so small that it's insignificant. The geometry of it is insignificant. So, all right. Well, now what if we have to consider the geometry? Well, in this case, we do have to consider the geometry because the charge exists along a circle, and so it's going to change as you're going to have basically infinitely many sums as you move across the circle, because you have one distance here, and then you're going to have another distance, and you're going to have another distance, and then yet another distance, and so on. Infinitely many distance away from the charges. Now, you might say, well, doesn't that mean the voltage is zero? Not necessarily. I'm sorry, infinite? No, that's actually not true. Sometimes it would be. It depends on how things work out, but in some cases, but in this case, it's not going to be infinite. So, and I'll show you why. So how do we deal with this? Well, when it comes to infinitudes, we usually use calculus, right? So and with geometries, it's best to use calculus. So that's what we're going to do. I'm going to start off with showing you another way to write voltage, though. So let's say if we wanted to rewrite voltage, and let's just keep it this way, right? Well, we can rewrite it as if it was just the magnitude of the electric field multiplied by R, right? And because the electric field is a spatial relationship, right? So in this case, it kind of inspires a volumetric or geometric sense of calculating the voltage. So that's good. So the next thing we want to do is, okay, how do we get from here to here? Well, we don't really know what the electric field distribution is, but we can find some type of distribution in a geometric sense. So, but suppose we were going to use this directly. Well, you'll notice that you're actually going to get zero. So, let's say if we call this dV equals, let's say if you were trying to use calculus directly on this, we'll get this, right? Well, R is a constant, so this will go to zero. But remember I said sometimes it does go to zero because of the infinitudes, so that's not going to work out. Instead, it's good to just relate the geometry directly. That's what you're going to be doing most of the time with these problems. So, for example, what we can do is if we're just given, let's just say just this, we can call the distance from the center of the circle to the point P, a point P, we can call it x bar, right? So that distance is x bar. And then also the radius, we can call it a of the circle. And then the distance from one point to the other is little r. Okay, so if we wanted to try to relate the geometry to something infinitesimal, what we can do is we can blow up a piece. So so we can take a piece of the geometry and try to find some kind of differential relationship, right? Well, we definitely know this is circular, right? It's going to have a charge distribution lambda, which is in units. Well, units are going to be the charge, which is in coulombs, and then it's going to be divided by the length, which is going to be in meters. Those are the units. And so we also have an angle here and a length. And so what we can do is we can just say d, and we also have a q along here too, right? So what we can do is we can say that q is going to be charge over length times the length, and the length is the circular area, or the circular length, which is just going to be a kind of like a circumference, right? So it'd be a lambda times theta times r, right? Alright, so this is it, right? So now what if we wanted to, okay, well you might say, well, why do I need this? Alright, well, what if we go back to our formula, right? So let me erase this part. Let's go back to the formula. So V, remember it was equal to K Q over R, but it can also be seen as if it's a differential volume, right? Or sorry, voltage. So we can then say that this is going to be dV equals K dQ R, right? Well, in that case, we have a Q relationship, right? Now let me ask you something. If we were going to replace Q directly, is that going to work? Well, what we would have to do is we'd have to assume that neither of the parameter of Q are changing. But in this case, we see that theta can change, but R can't. So if theta can change, we still conventionally need it because some circumstances you're not going to get the right formula for voltage, and it's just going to be a mess. So anyway, we're going to be using the calculus version, the infinitesimal, and well, it turns out you can actually plug it in this case, but actually no, I don't think you can. No, you can't. Well, let me erase this. This should actually be A. Sorry. I think you can, but let's go through the calculus details because that'll give us all the answers. So we have this Q here, dQ, right? And so what we can do is we can find what dQ is, because we know Q is lambda theta A, right? So dQ is going to be, let me erase this. So dQ is going to be theta A d theta, right? So that means that from the equation dV is going to be K dQ over R, but it's also going to be equal to K lambda A d theta over R. And so you can see that. So what do we do next? Well, what we're doing is if we're going to be taking the voltage at this point, remember we're going to be summing infinitely many points. So, but along the circle, and so theta would just go from here. It'd be like a polar to pi over 4 to pi over 2, 3 pi over 4 to 2 pi. Did I say that right? 3 pi over 4. I'm sorry, not 3 pi over 4. I messed up? Sorry. This is basic crap. Well, I mean, you just, sorry, 3 pi over 2. 3 pi over 2, sorry. Yeah, so, again, pi over 4, pi over 2, 3 pi over 4, and 2 pi. And so so now the next thing you got to do is you got to say, okay, I'm going to raise this part. So the integral is now going to be from 0 to 2 pi k lambda a d theta. But remember, the only variable we have is theta, and neither of the, everything else is a constant. So that's just going to be theta k lambda a over r from 0 to 2 pi, which means you're just multiplying by 2 pi, essentially. So take this mess. Now let's formalize it. Say VP is going to be, now it's going to be 2 pi over r k lambda a. Now this form, you may not like this form, which is okay because you can change it because of lambda happens to be, remember, it's length or charge over length, right? So it happens to be the total charge over 2 pi a, right? If you plug that back in, that means that you get that. Vp is going to be the total charge, and so because you plug it in for lambda, right? Divided by 2 pi a times 2 pi k a over r, right? And so the a's cancel, k doesn't cancel, the 2 pi cancels, and we're left with, funny enough, right, after all this work, the sum of the charge, or divided by r times k. So that would be Vp. And you're saying, well, that looks exactly like a point charge. Yes, it does. Coincidence? I think yes. All right. Well, this is what the formula is, so hope you enjoy that. And I think earlier I said that you basically, in this case, you could have plugged it in, but don't develop that habit. It's not good. Anyways, thank you for watching.